We received funding by the Department of Energy of the federal government in Australia to perform this study on the benefits of coral-free materials in Australia. And here we address just a part of the picture that we analyze. So fundamentally, if supercool materials can contribute to event heat mitigation and what they can do with regards to ventilation, and with respect to ventilation, what are the mechanisms involved? So in other words, why we are talking about radiation in a ventilation webinar. So we'd like to acknowledge the department with Stanford, Tanya, Kat, and Kavia who supported us, and then the project has been contributed by a large team at UNSW and many international partner investigators. All the project results are on the project webpage, which Maria put the link to in the chat, and many results have been recently published in this Energy and Buildings journal paper. So as I said, the project scope is vast, but here we are focusing on just the urban heat mitigation and the cooling energy savings aspects. So what have we done? First, we performed mesoscale climate simulations in several Australian cities and with the existing situation. So no co-roofing, just the normal low reflectance roofing that is commonly used here in Australia. Then instead with the co-roofing, and then we analyze the cooling demand, the heating penalty, and then so with the an ideal energy, an ideal HVAC, and then analyzing in floating condition, and finally the reduction in peak electricity demand and the advantage in terms of improvement of the performance of the efficiency of the HVAC system. So first, and here I'm showing something for Sydney. We took weather data from the Bureau of Meteorology, and we compared the results of the simulations in the base case scenario with measured data. So we had a model validation with a good agreement, and the simulations have been performed at a fine scale with the inner domain with grid cells of 500 meters by 500 meters. So very high resolution. And then so once we set up the model of the mesoscale, we also look after the selection of building models, considering 17 archetypical buildings pre-code, namely before the introduction of the National Construction Code in Australia, and then with a new constructions, namely with new insulation levels comprising offices, retail, schools, houses, and apartment buildings. For them, we considered a conventional roof with an albedo of 15% and a co-roof with an albedo of 85%, so a super cool material. In all cases, an emissivity of 85%. With pre-code, we mean no insulation, as it was common in Australia not so far ago, not so long ago, and with new insulation levels depending on the climate zone. And in terms of occupancy and internal heat gains, we follow the National Construction Code, but it's fundamentally very similar to ASHRAE guidelines. In terms of simulations, we used Energy Plus, and as we said, we computed the heating and cooling energy needs. Therefore, with an ideal HVAC with COP1, set point for heating 20 and cooling at 25. And then in one scenario, and then another scenario in free floating, just to compute the indoor air temperature. In all cases, we considered mitigated and unmitigated condition with regards to climate for just 2 summer months for January and February 2017, because of course mesoscale modeling has a huge computational load, so it's difficult to run simulations longer than 2 months, which is already a lot. And like before, in the unmitigated scenarios, all roofs have an albedo of 15%, and in the mitigation scenarios, roofs have an albedo of 85%. Then also we perform all year simulations with the data from Bureau of Meteorology, again for the same period. Why did we pick that year? Because it comprises some heat waves. It's not the absolute peak, but it's something very similar to a design summer year, but with real weather data series. Which cities did we take into consideration? So all main capital cities: Sydney, Melbourne, Brisbane, Perth, Adelaide, and for them we perform for these 5 capital cities we perform mesoscale simulations. For Sydney, considering 11 stations, 7 from Brisbane, etc., etc. And then only for Darwin, Alice Springs, and Hobart in Tasmania, we we didn't perform WRF simulations because they are smaller urban settings, and we only used weather data from the Bureau of Meteorology results. So here I'm showing the air temperature distribution at 2 meters height during a typical hot summer day in Sydney at 2 p.m. And as you can see here, you have the eastern suburbs closest to the coast, having a low ambient temperature and increasing temperature as we move inland, where most of the urban expansion is occurring. So when we deploy, and most of the urban sprawl also is occurring, therefore we have the biggest drops in temperatures, not close, not in proximity to the sea, because they already received the sea breeze, but where we have the most of the urban sprawl and where we have the most of roofing also. And also we see here there are some hot areas, but we need some areas, some built-up areas with cool roofs to reduce the air temperature. When we look at land surface temperature, we see here that all these small areas here where there's some urban sprawl display some reduction, but of course we saw before the core of the air temperature reduction was concentrated where we have more built-up area. Of course, both in case of the land surface temperature and especially for the air temperature, you see that the temperature drop is not even. So we have some areas where the temperature drop is 0.9, some areas where it's 1.2 degrees, and up to 1.6 degrees. In other cities, is very similar. And what is this temperature drop due to? It is due to a reduction in the turbulence sensible heat, namely the convection from so the heat exchange between the surface and the air, warming up the urban atmosphere. And as you can see here, within the urban area, we have a drop of even 200 watts per square meter during the peak hours of the day. And as it is cooler, we also have a reduction in the turbulent latent heat. Because of the reduction of the sensible heat and the turbulence in the atmosphere, we have a reduction in the planet boundary layer. So as we can see here, during the planet boundary layer is not constant throughout the day. It's maximum during daytime, of course, because we have the most of the turbulence, and therefore when we deploy cool roofs citywide, we have a reduction in that turbulence, and therefore a reduction of the plant boundary layer height. Of course, there are some aspects to be considered, like the potential reduction in pollutant dilution, or the reduced cloud formation. However, this mechanism of reducing the plant boundary layer, it is very, very important, because it reduces very much the penetration of warm winds from inland. So when we have less, we reduce the surface temperatures of all the roofs, we have a reduced buoyancy. When we have a high buoyancy, this sucks in the air from the rural surroundings, and especially from inland. And in this case, in Sydney, we have a lot of warm air coming from inland. When we have roofs instead, these airflows are very much reduced, and instead the penetration of a sea breeze, which is cooler, is very much reduced. Therefore, we have a significant reduction in the wind speed, especially of warm winds. Therefore, this is one of the most important mechanisms contributing to the mitigation of the whole urban area. What are the consequences of this? The consequence is that, of course, lowering the air temperature, we have a significant reduction in the cooling energy needs of buildings. Here I'm showing uninsulated, so existing building stock. For an office building, this is just one of those 17 buildings that we displayed before. And here in the existing situation with conventional roofs with albedo 15% in the unmitigated climate, or with just one cool roof on some isolated building, so 85%, but still the climate is unmitigated, all the roofs around are non-cool, or all the roofs are reflective, like in this case, like in the scenario number 2, and we see the remarkable differences from, as you see here, what is the bottom of the scale here becomes higher than the top of the scale when we have the roofing. So we reductions from 34 inland closest to Western Sydney, so to 33 kilowatt hours per square meter per annum, to less than 20. So a very, very significant reduction. When we consider the whole year, we can have an appraisal of the heating penalty. Yes, there is some heating penalty, which is more than which is substantial, only in the coldest only in the coldest climates in Hobart, but anywhere else the total savings largely exceed the heating penalties. The cooling savings largely exceed the heating penalties, therefore we achieve total savings. So all over Australia. One very important thing to consider is that, okay, if you have a low-rise office without a roof insulation for an existing building, we can, with just that building having a cool roof, we can, for instance, in Sydney, achieve a cooling energy savings between 37 and 42%. When we deploy roofs everywhere, we achieve savings between 50 and 63%. So it's remarkable. So that is expected. The important thing to highlight here is that even if we have a high-rise office, therefore the roof footprint it's small compared to the net floor area, and it's the building envelope is insulated, so therefore it shouldn't the heat transfer through the building envelope is not big, as it can be expected. So we have a 10-floor building. Okay, if we just put one core roof on that building, the cooling energy savings are small, around 1%, depending on the city. But then if we apply core roofs everywhere, we are lowering the air temperature, and therefore we are achieving substantial savings because of reduced impact of ventilation, and therefore the intake of air by the air handling units, etc., etc. So this is true also in the case of shopping malls, namely when we have a high internal loads. So this is very important not to consider only standalone application of supercool materials on a single building, but have a systemic approach. And the same applies to houses with a remarkable savings. As we said, by reducing the outdoor temperatures, we are also reducing the temperatures to which the condensing units are exposed to, and therefore we improve their energy efficiency ratio. And this leads to substantial savings in terms of cooling load because of effective increase of the efficiency of the residential splits or any other system that we are considering, whether it's BRV or else. Without an air conditioning system, so in free floating mode, we see that the indoor air temperatures are greatly reduced, especially in uninsulated homes, so existing homes, with decreases in indoor air temperature by 2 to 5 or even 6 degrees, depending on the quality of the building and the location of the building. This is very important because the outdoor air temperatures during heat waves in Western Sydney reach values as high as 48 or 50 degrees during peak hours. During winter time, yes, there are some penalties in terms of or heating. However, those are modest. So this is considered to be acceptable, and therefore, and this is in the uninsulated case. Sorry, this is in the new case with the new levels of insulation. So these effects are contained. You might have thought that we messed up with the simulations and our results are exaggerated. However, previously we performed measurements. This is a paper first authored by our colleague Shamila, with measurements in more than 100 houses, mostly social housing, across New South Wales, so from Sydney coastal to Sydney inland to rural inland, with indoor air temperatures as high as 40 degrees without air conditioning. So this is vital for people who cannot afford to install and operate air conditioning during heat waves. And one of the main most important things is that by lowering the outdoor temperatures, we are increasing the number of hours when we can open the window and have actually natural ventilation. So, and one of the features of Australian cities is that we have very hot temperatures during the daytime and significant drops during the night. Therefore, natural ventilation is possible. This now, in the future, with climate change simulations, we saw that there's with the increasing urbanization, we risk of having higher outdoor temperatures even during the night without mitigation. So, getting very similar to the situation we observe in European cities, and this is for Milan, where during the past summer they had weeks or more than 1 week with outdoor temperature during the night within the urban environment higher than 26 degrees. Therefore, natural ventilation is very much hindered. If we deploy curves on a single larger scale building, we can already achieve savings and improve the performance of rooftop HVAC equipment, as we observed and computed in previous work. However, the most significant savings are achieved when we implement it citywide. So to conclude, by deploying supercool materials, we lower the penetration of warm winds from inland in coastal cities such as Sydney. We increase the potential of natural ventilation because we lower the outdoor temperatures, and we lower the air intake temperatures for air handling units to make up air, and also we have a higher effective ERs. The indirect effects are substantial, even for highly insulated buildings and high-rise buildings. And also we are lowering the peak indoor temperatures in houses by more than 4 degrees during heat waves, which is vital. So with this, I thank you for your attention.